we have a guest. Welcome. No, I'm joking. Can we speak Czech? Přednáška bude v angličtině, ale jenom jsem chtěl říct poznámku ke zkoušce, k předtermínu. Samozřejmě vás jsem tam našel, vy jste tam 2 doktoranti, ale nevím, který jste z těch 2. Jo, dobře. Ale jak jsme se domluvali, můžete přijít, není problém. Jenom zopakuju, že jsme říkali na začátku, že můžete používat jakoukoliv literaturu, včetně svých počítačů, nebo jestli máte jaký chytrý mobil, nebo co máte, něco tam máte, nějaké poznámky v tom pravděpodobně, jestli v tom máte nakopírované nějaké cvičení nebo cokoliv. Všechno, kromě umělé inteligence, kterou byste si mohli otevřít a zadat si tam do toho zadání, jak to za vás počítá, tak to opravdu ne. Ale máte na to 3 hodiny, což jste už poznali z té aplikace, kde se přihlašujete. A doporučuji podívat se na to, co jsme tady dělali 2 přednášky zpátky, to potrubí přes řeku. Teplota na konci požadovaná. Chladí se to ve vodě, která protéká přes to potrubí a navrhnout se musí tepelná izolace tak, aby ta teplota na konci byla opravdu v té limitované hodnotě minimální. Myslím, že jsem řekl dost, že? Jo. A kromě toho ještě úplně poslední věc, kterou dneska budeme dělat, tak na to se potom taky ještě podívejte. Úplně poslední. Tak. Radiation. Last lecture we began talking about radiation heat transfer. You know, unlike conduction and convection, in conduction and convection we always can say about heat is transferred from one location, which is warmer, to another colder location. Warmer position, location, spot to colder. Not in radiation. Radiation very difficult to understand and very different from conduction and convection. I want to focus on this fact that it is really very different mode of heat transfer. It is exchange. It's not heat transfer, it is exchange. I radiate to you, you radiate to me. It is mutual exchange of radiative fluxes, exchange between different objects. That's the problem with radiation. Because every object which has temperature above 0 Kelvin radiates. I radiate probably a little bit more than you radiate to me. It depends on the visibility of objects. My body can see very well your body, but not so well the floor. It means the radiation between my body and the floor is less than between me and your body, because I can see you much better than I see the floor or the ceiling. So in radiation we have similar to Fourier law for conduction and Newton Coulomb law for convection. We have also basic law. Sometimes it's called constitutive law. Stefan Boltzmann law, you can see on the slide. And we distinguish between reference or ideal black body and all other bodies which are not black. Black body is theoretical body. In practice, you can find bodies which approach black body, but never you can meet bodies that are perfectly black in practice. So this Stefan Boltzmann law says that emissive power, EB, temperature is always in Kelvin, in radiation, always Kelvin. So it is in watts per meter square. And sigma is Stefan-Boltzmann constant. With the value, you can see 5.67 10 to minus 8, Stefan-Boltzmann constant. So this is the basic law for radiative exchange. Then when we talk about real body, this is emissive power. EB. Then we talk about emissive power of non-black body. We introduce concept of so-called gray body. Real body emits in very non-continuous spectrum, wavelength spectrum. I think that I showed last lecture. Yeah, something like that. You can see this is the real body which emits in the wavelength spectrum in a very non-continuous way. But we introduce concept of gray body, which means that we replace the real surface by gray body surface, which emits in a continuous spectrum of wavelengths. So gray body is a really technical word which replaces real surface, and then we talk about emissive power of gray body, which is always less than 1. 1 is for black body, and epsilon is called emissivity of the surface. Emissivity. You can find this value in tables. Emissivity of metal, non-metal, anything. Any material, you can find in tables, and you can find emissivities of different materials. So this is the gray body. And what it means that emissivity is a ratio of emissive power of this gray body to emissivity of black body, emissivity of the ideal reference body. What else to say? Okay, then we talk about what happens with irradiation of the surface. G is irradiation. Ozáření. I mean, energy, radiated energy, which hits the surface, which is incident on the surface. And part can be absorbed. Then we talk about absorptance, absorptivity, in English, absorptivity. Part is reflected. We talk about reflectivity. And part can be transmitted, yeah, transmitted, okay, transmitted, transmissivity. So in industrial practice, transmittivity is taken 0 because it is applied only for transparent surfaces, as glass, plexiglass, and so on. So then we use very simple equation that absorptivity and reflectivity equals 1. It means if 1000 watts hits the surface, this 1000 watts must be split into something is reflected, something is absorbed, something could be transmitted. So if transmittivity is 0, then must A plus RB equals 1. So, and one more important relation For any calculations in radiation, this is probably most important parameter, emissivity of the surface. It says us how much emissive power is produced by the surface. So you can find, as I mentioned before, in tables. But in practical calculation, we also need to know how much energy is absorbed, because absorbed energy increases the temperature of the body. So we need to know how much energy from the incident energy is absorbed by the body. And to calculate absorptivity is very complicated because it depends on the radiation. Radiation can come from very different sources from the whole environment. So it is complicated to calculate absorptivity, but it's very easy to measure emissivity. And there is one law called Kirchhoff law, that says that emissivity equals absorptivity, and it helps in calculations. But this Kirchhoff law applies in situations when temperature are in the space we deal with are not very different. So it means you cannot apply this law for example, solar radiation, because solar radiation means that the source, sun, has very high temperature, about 5,000 Kelvin, something like that. So, and also, as I mentioned last lecture, it cannot be applied for example, when you calculate something in welding. I mean, welding arc has also very high temperature. So now there are very special cases in which you can't use Kirchhoff law, but in most of practical application energy, you can use this law and say, okay, absorptivity equals emissivity. So that's all as for the introduction to radiation. Now, radiation exchange, radiation transfer, let's say transfer between two surfaces. Let's take these two surfaces, something like that. Or two objects. Object number one, or surface number one, surface number two. We know surface area, S1, we know temperature T1. Let's say that temperature T1 equals 400 Kelvin. Then we have surface number two, with temperature 2T equals, for example, 300 Kelvin. And surfaces are the same, let's say 1 meter square. What happens if we look at the situation from the point of radiation? So each surface, it is black surface, emits emissive power for black body, you see on the right side of the board, sigma T1 force power. Surface number two emits EB2, sigma T2 force power. It is what is emitted because I mentioned last lecture that surface emits into any surface emits into hemisphere. When we pitch a hemisphere above the surface emits in all directions within this hemisphere. So now we are looking for what is exchanged by radiation between surface 1 and surface 2. So what is the heat? what is radiative heat exchange, heat flow rate exchange between, net, we call it net exchange. Net, čistý, net. Okay, let's look at surface number 1. So we are interested in what is exchange between 1 and 2. Surface number 1 emits EB1, which is S1 EB1, total in watts. Surface multiplied by emissive power of black body number 1, or black surface number 1. It means S1 sigma T force power. It is in what is emitted from the surface number 1. But the question is, how much from this emitted power hits the surface number 2? We can emit, for example, 1000 watts, but this 1000 watts go to anywhere. It means that to surface number 2 goes only a fraction of what is emitted by the surface number 1. And it means that S2 receives only fraction, which we call view angle later, multiplied by S1 EB1. And this value, F12, is called view angle, or in Czech uhlový faktor. It means that view factor is defined as a ratio what is received by the surface number 2. This arrow 2, number 2 means received, compared to what goes out from the surface number 1. So the arrow always means to or out. We can continue. So it is F12 multiplied by S1 sigma T1 force power. Now we look the same way to surface number 2. Surface number 2 emits S2 EB2, which equals S2 sigma T2 force power. But surface number 1 receives only fraction of what is emitted by the surface number 2. It means S1 receives only F21, from the view from surface number 2 to surface number 1. That's why we say F2 multiplied by S2 sigma T2 force power. And now the total exchange or net exchange is difference between these two rates. It means Q12 is what is emitted by surface number 1 and received by surface number 2 minus what is emitted by surface number 2 and received by the surface number 1. It means I give you 1,000, you give me 500. Net exchange is 500 from me. That's the idea of the exchange. My vice versa, you give me 1,000, I give you 500. No, it's something like that. I give you, you give me, and difference is a net exchange. So Q1 to 2 is 1 to 2, I mean F1 to 2, S1 EB1 minus F to 1, S2 EB2. Or when you use Stefan Boltzmann law, we can express this emissive power as sigma temperature T1 force power minus F21 S2 sigma T2 force power. So it is almost final equation how to calculate exchange, radiative exchange between two objects or two surfaces. But we can simplify. We can assume that temperature T1 equals temperature T2. In that situation, exchange Q12 is 0. And when you look at this equation, and this right side equals 0, then we can cancel temperatures. And we get very simple formula. S1 F12 equals S2 F21. This is a very important formula, which is very often used in radiation calculations. We call it reciprocity rule. Reciprocity rule, český vztah reciprocity. Vztah reciprocity. You know, this formula is important in practice. When you take situation of two concentric cylinders, for example. This is surface number 1, and this is surface number 2. I mean, surface number 1, external surface of object number 1, and internal surface of the object number 2. What would you say equals F12? The question can be asked different way. How much energy emitted by surface 1 goes to surface number 2? Let's say surface number 1 is some kind of electric radiator, 1,000 watts. These 1,000 watts go where? Only to surface number 2. It means that VU factor 1 to 2 equals 1. Everything goes from 1 to 2. But what we can say about F21? When we move from surface number 1 to surface number 2, now we stay on the surface number 2 and look around. What we can see? We can see surface number 1, but also we can see ourselves. So we cannot say that is equals also 1. We can use this reciprocity formula to calculate what is F21. So it is F12 multiplied by the ratio of the surfaces, S1 to, oh, that's 10. So this is particular situation where this reciprocity rule can be used or must or should be used. So this is the reciprocity rule. If we apply this reciprocity rule, then we can rewrite the net radiative exchange that with these two replaced by these two. So it means we get F12 S1 sigma multiplied by difference of force power temperature of temperatures. So this is the final formula. How to calculate net radiative exchange between two surfaces or two bodies using reciprocity rule to simplify this equation we came to when we apply this what gives surface number 1 and receives number 2, or it gives us surface number 2 and receives surface number 1. So this is very simple equation and very often used to calculate radiative exchange between two objects or two surfaces. Concerning the view angle F12, you can find this value for many different configurations in tables or graphs. So it is value tabulated value or the values that you can find it graphs or plots or tables. And what else? Yeah, one important thing. This formula can be rewritten in the form with resistance. It means we can rewrite sigma multiplied by temperature difference, T1 force power minus T2 force power, divided by 1 divided S1 F12. And this is called space resistance. Space resistance. Prostorový odpor, check prostorový odpor. Space resistance. Because it reflects the orientation of surfaces in the space. You can see if we have the same temperature difference, T1 and T2, and different orientation of surfaces, if the visibility between surfaces, which is reflected by the value of angle view, so if the visibility is very bad, then the view factor is low. We have high space resistance, and for the same temperature, the net exchange will be lower. So it means the better orientation of objects in the space means that we, in the same temperature difference, transfer less energy than if visibility is better. So that's the problem with radiation, that visibility is very important. So visibility is only geometrical factor between the objects. Nothing has nothing common with mathematics. It's just geometrical factor, the geometrical visibility of the objects. So space resistance is a leading factor, or it controls the net rate exchange between objects with temperature T1 and T2. So now when we look at our example, so you can find for this orientation that, for example, F12 you can find equals 0.5. It depends on the angle between these surfaces and also the area of the surfaces. But let's say that we found the value F21 equals 0.5. Then we can calculate net exchange as 0.5. It is F12 multiplied by the surface equals 1, multiplied by Stefan Boltzmann constant, 5.67 multiplied by 10 to 8, and difference 400 Kelvin to force power minus 300 Kelvin to force power, and we get a value 496 watts. So if the view factor is less than 0. Let's say 0.2, we get 5 times lower value of net exchange. So you see that really the view factor, view angle is control parameter, leading parameter which control the transfer, net transfer of radiative energies. So let's continue. We know reciprocity rule, reciprocity. Now there is a second rule which is very important also in calculations of radiative exchange. It is called summation rule. Český sumační pravidlo. Let's have an object, let's say the cylinder, something like that. This is surface S2, temperature T2. This is surface S1, temperature T1. Radius R1. And the height of the vessel, or what is, let's say the vessel, it's a container or vessel, H. And the surface, number 3, with temperature T3, is a cylindrical surface. These are, let's say, bottom and floor of the container and cylinder walls. So let's say that we heat the surface number 1 by certain power. Maybe could be considered as an electrical heater, or maybe could be a series of gas burners on the floor, on the container. Could be some chemical furnace, some kind of furnace with series of burners, hořáku burners on the bottom of the container. So we can calculate in some way the energy which comes from the burners, from the burning gas to this furnace. So energy which is emitted from the surface number 1 must go to surface number. In case the surface number 1 is convex or convex, vidutý, convex or concave, convex. So if the surface number 1 is convex, then energy can go from 1 to 1, also. But it's very rare situation. But theoretically should be there that also part of the energy emitted from 1 goes to 1. Plus goes to 2, plus goes to 3. Nothing else. Because in this situation, in this arrangement, we have all 3 surfaces. One, which is the original surface which emits the energy, which releases the energy, to surface number 2 and surface number 3. So if we divide but what is emitted from the surface number 1, we get 1 equals energy which goes to 1 from 1 plus energy which goes to 2 from 1 plus energy which goes to 3 to what goes from 1. And these are view factors. 1 to 1, 1 to 2, 1 to 3. If you remember from the first board, I mean, what I wrote on the left side at the beginning. So this is definition of view factor or angle view factor or angle view. So different names are used for that. From this formula, we see that sum of view factors towards towards a specific surface must equal 1. The same if we move from surface number 1 to surface number 2. Now we sit on the surface number 2 and look down. We see from 2 surface 3 and surface 1. So we can write the same equation. Energy which goes from 2 goes to 1, goes also to 2 if the surface number 2 is convex. So from 2, F which goes from 2 goes to 2 as well, but goes to 3 and goes to 1. So for each surface, we can apply this summation rule. That's the problem, as I mentioned at the beginning. Radiation is exchange. We have to deal with all surfaces in the radiation, not only with the warmer one, as for conduction or convection. So that's the problem which radiates means. So what to say? Okay, so for example, in this arrangement, the question could be, what is the angle view want to say? In engineering meaning, I ask what percentage of energy that is emitted from surface 1 goes to surface number 3. It is question I ask different way. When you look at this configuration, what would you say? Let's say 1,000 watts is generated by this let's say gas burners or electrical heaters. How much from this 1,000 watts go to number 2 and number 3? 50%, 30%, 20%. Do you think that also the distance between these platforms plays a role? If the height is larger, probably also radius plays a role. It is, if the container is very thick, a large diameter, very short, or very high and very slim, then it's a bit different. So then, again in tables or graphs, you can find F12. F12 from tables equals, for example, 0.3. Just an example. You can find tables that F12. In tables, you can find, for example, the cylindrical platforms, very different radius, different distance. You can also find platforms with different diameters, large diameter, small diameter, and so on. So all values for these cylindrical surfaces can be found in tables. Let's say we find 0.3. What does it mean? That 30% what is generated by surface number 1 goes to surface number 2, and 70% goes to the cylindrical wall. So that's because we use this summation rule. If we know F12, we know that F12 plus F13 equals 1, because we don't expect that there is any reasonable value of F1 to 1. So we use summation rule. So one value we can find in tables. The second value can be calculated from the summation rule. So And now, between two surfaces, between 3 and more surfaces. Let's take typical 3 surface configuration, something like that. This is surface number 1, temperature T1, surface number 2, temperature T2, surface number 3, temperature T3. And the question is, what will be the power which must be brought to surface number 1 to keep these temperatures? So, we know from balance that what we bring to surface number 1 will be sum of what is exchanged between 1 and 2 and what is exchanged between 1 and 3. Nothing else, because there are 3 surfaces and they exchange between each other. It means if we bring 1000 watts, this 1000 watts go partly to surface number 2, it is exchanged between 1 and 2, and partly goes to 3, exchange between 1 and 3. So, we can apply what was for 2 surfaces, because now we know how to calculate Q1 to 2 and Q1 to 3. It is EB1 minus EB2 divided by space resistance 1 to 2 plus EB1 minus EB3 divided by space resistance 1 to 3. So it is, if we have only 2 surfaces, then we apply only this part of the equation. But now we have to have 3 surfaces. It means we have to take into account exchange between 1, 2, 1, 3. And so we can rewrite using Stefan Boltzmann law, sigma T1 force minus T2 force. Sigma T1 4 minus T2 4 divided by space resistance between 1 and 2, 1 divided by S1 F12 plus sigma T1 force power minus T3 force power divided by 1 divided by S1 F13. So that's all. If we make 4 surfaces, 5 surfaces, n surfaces, we just add other equations, I mean other terms on the right side. So as many surfaces we have, so many terms on the right side we can write down. So this is this is about black objects or black surfaces. But now let's change to gray surface. So radiation exchange between 2 gray surfaces. Gray surfaces, it is important. because now situation will be quite complicated. Last lecture we introduced a value called radiosity of the surface. You may remember that if we take a surface, this is irradiation with what hits the surface. Part is reflected, but also there is a emission from the surface. Because it is gray surface emit epsilon multiplied by emissive power of black body. If it is black body, it is emit only EB, given by Stefan Boltzmann law. But because it is gray surface, it always emits less, because emissivity is always lower than 1. So, and the sum of these two components, what is reflected from incident radiation, plus what is emitted by the gray surface, is called radiosity. Radiosity. And we use J for radiosity. J is sum what is emitted by the gray surface plus what is reflected from the incident radiation. And if we apply that sum of absorptivity and reflectivity equals 1, and also that absorptivity equals epsilon according to Kirchhoff's law, then we can simplify, we can rewrite this definition of radiosity as epsilon multiplied by EB plus 1 minus epsilon multiplied by G. So this is definition of radiosity. We say it is radiative energy which leaves the surface. Also in Czech we say energie, která opouští povrch. So it is technical term, energy which leaves the surface. It is sum of what is emitted plus what is reflected. If we have black body, there is no reflection, and there is only what is incident on the surface is emitted. No way, because it's a black surface. Black surface absorbs anything and emits. There is no reflection. So, gray body is complicated because part of energy incident on the surface is reflected. And of course, the surface itself also radiates by this value. So, from this equation, we can express incident, irradiation, which equals J radiosity minus epsilon EB divided by 1 minus epsilon. It is what applies for a given surface. This equation applies for a given surface, and it is just we express the irradiation from this equation. But then we also have a balance equation on the surface. Balance equation which says that heat, radiative heat flux, small q dot, which is total rate divided by surface, it is difference between what leaves the surface minus what is incident on the surface. Let's say that we have a surface and 1000 watts leaves the surface. 1000 watts means it is the sum of what is reflected and what is emitted. 1000 watts. But the surface also receives energy from other objects. Let's say it receives, we leave 1000 watts, but they receive 500 watts only. So the net flux, we have to add something from the heating, from burners, whatever. So it is, balance equation means that that what we have to bring to the surface is the difference what leaves the surface minus what receives the surface, J minus G. So if we rewrite using this formula, sorry, this one, we get epsilon EB plus 1 minus epsilon G minus G, which can be rewritten for Q equals S multiplied by J minus G. It's just manipulation with the surface, because this value is in watts per meter square, and this value is in watts. That is the only difference. So we get very simple manipulation, simple calculation. We get for the total amount of energy which must be brought to the surface to compensate for this difference equals epsilon multiplied by S divided by 1 minus epsilon divided multiplied by EB minus J, which can be written in this way, divided by 1 minus epsilon divided by epsilon S. And this is very important formula. And this denominator in the fraction is called surface resistance. It is so I rewrite this formula on the left side of the board. It means Q equals EB minus J divided by 1 minus epsilon divided by S epsilon. And this is the we call it surface resistance. Why surface resistance? You know, we introduce, this is the basic surface. And the basic node is emissive power of black bodies. Then, but we don't have black body, we have gray body. And you know, it is, if we have a black body, then we emit EB equals this value. But if we have gray body, the surface leaves this value. Some of what is reflected, some what is emitted by gray body. So we introduce so-called fictitious surface. Fiktivní surface, fiktivní povrch, on which we have radiosity J. What to say? You know, in between there is a surface resistance. Surface resistance equal 1 minus epsilon divided by epsilon S. It is a kind of grayness resistance, because grayness means that compared to black surface, this surface, represents surface resistance compared to black body. So it means, in other words, gray surface is worse as for as a quality than black surface. And the fact that gray surface is worse is reflected or expressed by the surface resistance with emissivity is 1. If we have black surface, there is no surface resistance. Only with gray surfaces we introduce surface resistance, which reflects the grayness of the surface. You see that emissivity, if the emissivity is very low, then the resistance will be higher. So it is concept, I mean this resistance, surface resistance and space resistance is a new concept in radiation introduced in some maybe mid-50s, 1950s, something like, by American scientists, I can't remember the name. But before this concept was introduced to the heat transfer community, it was very complicated to explain the situation with gray surfaces, to explain how gray surface behaves. So this resistance simplified the understanding of the problem of gray surface. So if we have two surfaces, let's say one surface, something like that, and we have a second surface, something like that, surface number 1, surface number 2, then at each surface, we draw a fictitious surface. And the potential on the surface number 1 is EB. Then we have EB1. We have a fictitious surface, and between them, we have a surface resistance, R1. R1 equals 1 minus epsilon 1 divided by S1 epsilon 1. The same on the surface number 2. We have a potential EB2, then fictitious surface on which we have radiosity J2. It means energy which leaves the surface. J2 is a sum. So that's why we replace for black surface this one, we replace by this complex formula. So we talk now, in this gray surface, we talk not only, not about emissive power, black body, but we talk about radiosity, energy which leaves the surface. And in between this potential, we have a space resistance, R1 to 2, which one equals 1 divided by S1 F12. And this is R2 equals 1 minus epsilon 2 divided by S2 epsilon 2. So now for exchange of energy between two gray bodies, we can write quite simple equation. Now it is similar to conduction heat transfer between across 3 layers, for example. Quite similar, not the same, but similar. Yeah. What about the exchange now? We have surface number 1 and surface number 2. The question is, what will be the exchange between 1 and 2? Q1 to 2. Similar to black body. We say, okay, surface number 2 surface number 2 leaves J1, S1. Is it correct? Because what leaves the surface number 1 is radiosity J1 multiplied by surface number 1 in watts. but receives surface number 2 is F12J1S1. The same view factor. It means 1000 watts leaves the surface number 1, but surface number 2 maybe only 500 receives, because the view factor between surface number 1 and surface number 2. Now we move from 1 to 2. We make the same. What leaves the surface number 2? Leaves J2, S2, but receives F21, J2, S2. And difference between these two values is a net exchange between two gray bodies, two gray surfaces. It means Q12 is what is received by surface number 2 from what leaves the surface number 1, minus what receives surface number 1 from what leaves the surface number 2. I mean, when I explain by words, it looks, sounds complicated, but it's very simple. I take into account what is received by surface 2 from what leaves the surface number 1, and what receives surface number 1 for what leaves the surface number 2. So it is quite simple, but you have to combine this leaves and receives. So is then this a difference? J1, S1, F12 minus J2, S2, F1, F221. You know, I warned you at the beginning, radiation is very complicated mode of heat transfer. It's not so easy. But I think that in total, it's, if you understand the resistance scheme, it's very simple to understand this exchange, even with gray surfaces. So if we use a reciprocal rule, saying that S1 F12 equals S2 F21, we can simplify the equation for Q12, and we write S1 F12 multiplied by differences in radiosities. If you remind black body, the formula is quite same, but instead of J, we have EB. For black body. So we see that formally is the same. Instead of emissive EB, now we work with radiosity J, but it's the same. But we can rewrite this equation for Q12, again introducing resistance. Means difference J1 minus J2, and we put S1 F12 in the denominator, and it is space resistance. Same as was in with black bodies. So space resistance doesn't depend on if you deal with black or gray body, because it's just purely geometrical factor, how surfaces can see each other. It means the space resistance will be always the same, no matter we talk about black or gray body. It is just geometrical space factor. And now when we look at this resistance scheme between two bodies, so we say, okay, this energy which must be brought to surface number 1 and to keep temperatures of surface 1 and surface 2, we can calculate the total exchange rate, which goes between 1 and 2. And in all directions, we have to cross surface resistance number 1, space resistance, surface resistance of surface number 2. It means we apply equation between this node and this node. And everything must cross 3 resistances: surface, space, surface. It means we write this equation as a difference EB1 minus EB2. And between these basic nodes, we have surface resistance, space resistance, surface resistance. It means 1 minus epsilon 1, S1 epsilon 1. This is the surface resistance, R1, plus space resistance, R1 to 2, plus second surface resistance of the second surface, 1 minus epsilon 2 divided by S2 epsilon 2 is surface resistance R2. So it is not so complicated. You see that this is simply calculated by Stefan Boltzmann law. And these resistances can be epsilon, you can find in tables, emissivity of the surface number 1 and surface number 2, emissivity epsilon 1, epsilon 2 are known. You can find in tables view factor F12. So we can easily, at the beginning of calculations, calculate all resistances. And if you know temperatures, you can get the value of radiative, the flux radiative, radiation rate exchange between two gray surfaces, because this is value in watts. Now, there is one special case which is very often used in practice. Special case which simplify the equation I just wrote down. When we look at this formula, we can have a situation that we have a small object enclosed in a large space. If there is a, for example, coal oven here, sporák, in a large space. So this is very special situation in which you can say, okay, S1 is much less than S2. And if you look at the formula, we can rewrite the formula for Q1 to 2 that we take surface S1 and manipulate with the denominator. It means 1 minus epsilon 1 divided by epsilon 1 plus, what's the view factor F12? 1. Yeah, sure, 1. Because everything what is emitted or what leaves the surface number 1 goes to surface number 2. It means F12 equals 1. If the source emits 1000 watts, this 1000 watts go to solely to surface number 2, nowhere else. It means when you look at this equation over there, and we put S1 in a denominator. Čizatel? Denominator is jmenovatel. What is down? What is below? And what it is? Numerator. Sorry, numerator. Denominator and numerator. Yeah. So if we put S1 to numerator, then we simplify what is in denominator plus ratio of surfaces multiplied by 1 minus epsilon 2 divided by epsilon 2. So, and because S1 is much less than S2, we can cancel this term, and we can manipulate with two terms, because it is 1 divided epsilon 1 minus 1. Minus 1 plus 1 is 0. So we get very simple formula. Epsilon 1 sigma S1 multiplied by temperature difference. This is a very simple formula which can be applied in situation of small object enclosed and encapsulated in large space. So, well, I think that we can skip 3 and more surfaces. Yeah. Because I don't think that in your practice, I mean, after you will be hired by some company, hardly you can face a problem to calculate radiation between 3 and more surfaces, enclosed surfaces. It's a very special topic. I don't think it's worth to mention. Yeah. Instead, I think it's more useful for you to say something about combined mode of heat transfer. Combined mode of heat transfer is a situation which you can meet very frequently in practice. So let's stop with the radiation between two gray surfaces in a special situation. You know, just one moment. When we look at this formula, this equation, this can be applied also for radiation shield. I mean, radiation stínění. If we have one surface, number 1, surface number 2, and we want to reduce radiation from 1 to 2, you know, for example, when you sit in front of a fireplace in your room, home somewhere, the home in front of your fireplace, very often when you sit in front of the fire, you move further from because it's very hot, or you just, well, I do it in my room. I just put a small construction and put aluminum foil on that, just to shield the radiation. I mean, to shield my body, or my wife's body, from the radiation from the flame in the fireplace. It is radiation shield, so reduce radiative energy going from the fireplace to your body. So, and you can. So if you put additional surface between these two original surfaces with temperature 1 and temperature 2, each surface, on each surface you draw fictitious surface. So you have surface resistance, space resistance, surface resistance, space resistance, surface resistance. So you can add any number of resistances. The flux from the source meets on the way. So we have 1, 2, 3, 4 surface resistances and 2 space resistances. You just extend the denominator by one additional space resistance, because we have 2 spaces, and two additional surface resistances of the radiation shield. So you can still use this equation for a situation with as many radiation shields you want. Just you add as many resistances there are on the way from left to right side. Very simple. So if you understand the resistance scheme, we just add resistances. And you reduce this flux, because still you have the basic temperature difference, T1 and T2, but you add resistances. More resistances, you reduce heat flow rate. It's the same with conduction. As many resistances, conduction resistances you have, as many layers you have, you reduce the same temperature on the boundaries, you reduce heat flow rate. So resistances, what you add as a resistances, you increase heat flow rate transferred between basic surfaces. It is what I wanted to say at the end. That if you understand the resistance scheme, it's very simple to work with gray surfaces. So combined mode of heat transfer, what does it mean? What it means? Piece of cloth. Combined mode of heat transfer. Let's have a wall, metal wall of a maybe combustion chamber. On one side we have temperature T1W. This is the energy which comes from the left side. Question might be, what will be the energy which will be brought to the wall? On the external side of the wall, we have temperature TW2, the surface S, emissivity of the surface epsilon, because we will have to take into account also radiation, and environment with temperature T infinity, heat transfer coefficient, and surrounding walls with the same temperature as a surrounding air. This is environment, surrounding air. Surrounding air. So, when we bring certain energy power to the left side of the wall, this energy goes through the wall by conduction, reaches the external wall, and then it is transferred by convection to the surrounding air. This is temperature heat transfer coefficient, but also by radiation to the surrounding walls, surrounding walls of the space. So, if we draw resistance scheme, we have potential TW1, then we have conduction across the wall with resistance for the conduction R lambda 1. We reach temperature TW2. So we cross the wall by conduction. On the way, we must cross the resistance, conduction resistance. Then this flow which comes to this to the left wall splits partly. It goes through convection resistance and partly goes to through radiation resistance, resistance. And the final potential is temperature of the environment or surrounding walls. That is identical temperature. So what we do, we can write balance equation. We can write for Q1. First, we have to cross by conduction, this distance. Then there is a sum. What is transferred by convection? What is transferred by radiation to surrounding air or surrounding walls? That means conduction, first conduction. Q equals, you should remember conduction. Difference in temperature TW1 minus TW2 divided by thickness of the wall, let's say L, divided by thermoconductivity of the wall. It's maybe could be carbon steel, could be whatever, could be this is resistance to conduction, R lambda. Then convection, heat transfer coefficient multiplied by the surface, multiplied by temperature difference, TW2 minus T infinity, plus radiation. And we can use this formula. I erase the formula. The simplified formula for small objects enclosed in large space. You can assume that this chamber is placed in a large hall. It means that we can use the simplification of negligible surface of the whole object compared to large space in which the object is placed. So it means radiation epsilon multiplied by S multiplied by sigma TW1 force power minus T surrounding temperature force power. So what to do now? I mean, we are slowly approaching the end of the analysis. We can rewrite the formula for heat flow rate transferred from the left side to the right side as TW1 minus TW2 divided by conduction resistance remains the same. Equals TW2 minus T infinity minus 2 infinity divided by 1 divided by alpha S, which is resistance to heat convection, plus, and now we have a problem. We have the radiation. The formula for radiation heat flow rate. It is non-linear formula. We cannot express the formula in the similar form. Simple temperature difference divided by something which could be called resistance to radiation from the surface to surrounding wall. So, what to do? what to do. We express radiation flux, radiation heat flow rate, radiation heat rate, which equals epsilon sigma s multiplied by Tw2 force power minus T surrounding walls force power. We express this formula by means of Newton's law of cooling for convection with kind of radiation heat transfer coefficient alpha R multiplied by the surface multiplied by simple temperature difference Tw2 minus T surrounding walls. And from this equation, we express heat transfer coefficient by radiation. It is kind of artificial coefficient, which can be used then to write the similar formula for radiative transfer as for convection. It means that we can write, I mean, it is there is no complication. So, just manipulation with this equation. So, finally we can get the formula epsilon sigma multiplied by Tw2 plus T surrounding walls multiplied by Tw2 second power plus T surrounding walls force power. So this is the formula for radiation heat transfer coefficient. And now we can add plus Tw2 minus the surrounding divided by 1 divided by alpha Rs. This is resistance for radiation. So, and the final formula which we come to writes Q1 equals, okay. I erase the picture, again the picture. Tw1, Tw2, T surrounding equals T infinity. So resistance convection, resistance radiation. So we have one resistance for conduction, and we have parallel resistances, convection and radiation. That means the total formula is Tw1 minus T surrounding, which equals T in infinity, the same temperatures, divided by resistance to conduction plus equivalent resistance of these two parallel resistances. Because we split, we go this way and we go this way. So there are two parallel resistances from the point to Tw2. From this point Tw2 we split to two resistances. Part goes by convection, part goes by radiation to the same potential T surrounding or T infinity. So, and equivalent resistance is calculated simply simply as a sum over convection radiation plus, convection resistance plus radiation resistance to -1. That's all. The only problem in such arrangement is that to express radiation heat transfer coefficient, we need to know wall temperature TW2. If we assume that we know this temperature on the internal side, it is mostly, let's say, assumption, very realistic assumption that we know this temperature, and we know this temperature, then to calculate radiative heat transfer coefficient, we need to know this temperature. So it means that at the first step we guess. We guess what could be TW2, and the first approximation could be, okay, TW2 to calculate radiation heat transfer coefficient, that we say, okay, TW2 equals TW1. Difference could be sometimes very small, depending on the rate of the heat flow rate. But the walls are maybe, the wall could be centimeter, maybe 2 centimeters. So the difference between TW1 and TW2 cannot be very large. So the first step approximation, we assume, okay, TW2 equals TW1. We calculate radiative heat transfer coefficient, we calculate resistances, and we calculate Q1. If we know Q1, we can recalculate TW2 just from the conduction equation.
I think in the equivalent resistance there's a mistake. I think in the parentheses there should be 1 over R actually. No, it's just R.
Yeah. You are right, yeah. Is that correct?
I was just talking about the inverse. On the right-hand side, you have brackets, and then you have raised to the power -1, if I understand correctly.
Yeah, I'm stupid or what? No? Wait.
Those terms inside the bracket should be flipped over because 1 over alpha S is actually just resistance, but there needs to be 1 over resistance.
In general, equivalent resistance is calculated as a sum of reciprocal values to -1. It means 1 divided by R1 plus R2. Is it correct? R1, R2 to -1.
It should be 1 over R1 plus 1 over R2.
Yeah. Sorry, yeah. Something like, yeah. Okay, so, and is it correct now? Yeah. Why not not to write it in a complicated way. It could be written in a simple way, but the complicated way is very nice anyway. So sometimes, yeah. Yeah. Okay. I think that's all. Not only for today, but for your whole, not for this, it's for, yeah, it's the end of lectures, not the course. Course is going to be finished after examinations. So it's, I hope that you will be successful, you will succeed in examination. I will be happy to ascribe A to any one of you. One small joke, examination. Student comes to a classroom, sit down, and professor, any questions? The student, excuse me, what's the examination of the course today? What course is this examination? So it's... yeah. This was last lecture today, yeah? So next Tuesday, you have time to prepare for examination.